All right, today we're going to dive into the heart of digital design with a tale of two logics. We're going to unpack two really fundamental, but kind of opposite ways of describing how a circuit should behave: sum of products and product of sums.
But let's start with a bigger question. Say you have a set of rules. If this happens, then do that. How do you actually build a physical electronic circuit that just follows those rules automatically? Well, that's the core puzzle of digital logic. And the answer is all about turning those rules into a language that circuits can actually understand. And that language is Boolean Algebra. Okay, so let's get our hands dirty with a little logic puzzle. This thing here is called a truth table. All it does is list out every single possible combination of inputs. We've got A, B, and C, and then it shows us the output we want for each case. Our mission, should we choose to accept it, is to create one single, elegant Boolean expression that perfectly describes every rule in this table. And here's where things get interesting. This is where our two logics come into play. See, you can solve this puzzle by taking one of two completely different paths. You can focus only on the times the output is true, a 1, and describe what causes that. Or you can do the exact opposite. You can focus on all the times the output is false, a 0, and describe what causes that. The craziest part? Both paths will lead you to a totally correct answer. So let's explore that first path. We'll call this the optimist's path. It's all about being positive. This is the sum of products path, where we're going to focus exclusively on what makes our function true. The name sum of products pretty much tells you everything you need to know. In the world of Boolean algebra, sum is just a fancy word for the OR operation, and product is what we call the AND operation. So an SOP expression is just a bunch of AND terms that are all ORed together. You can think of it like this. This condition can make it true, or this condition can make it true, or this other one can make it true. Now, the basic building block for this whole method is something called a minterm. And a minterm has this really cool, unique power. It's an AND term that's specifically built to be true for only one single row of our truth table, and it's false for every other row. It's like a super specific key that only unlocks one single door. So how do we actually build this thing? It's a really simple three-step process. First, just scan down the truth table and find every single row where that output is a 1. Got it? Okay. Second, for each of those 1 rows, you write its unique minterm, and the rule is simple. If an input variable in that row is a 0, you use its opposite, its complement, which we write as A prime. If the input is a 1, you just use the variable as is. And finally, you just OR all of those minterms together. That's it. Let's actually do it with our puzzle. As you can see, we've got 3 rows where the output is 1. Okay, look at that first 1 row. The inputs are 0, 0, 1. So following our rule, this becomes A prime and B prime and C. We just do the exact same thing for the other 2 1 rows, creating a unique minterm for each one. Then we just stick them all together with ORs, and boom, that is our final sum of products expression. All right, so that's one path to the solution. Pretty cool, right? Now let's rewind and take the other path. We're going to solve the exact same puzzle, but this time we're going to do it by focusing on what makes the output false. This is the product of sums approach. And as you can probably guess, product of sums is basically the mirror image of what we just did. Product means and sum means OR. So a POS expression is just a set of OR terms that are all ANDed together. The logic here is totally different. It's the output is true only if this condition is met, and this condition is met, and so on. And the building block for POS is the maxterm. It's the perfect counterpart to the minterm we saw before. A maxterm is an OR term, and is specifically designed to be false for only one single row of the truth table, and it's true for all the others. It's kind of like a security check that fails for only one very specific ID. The process feels really similar to SOP, but there's a critical twist. First, you identify every row where the output is a 0. Simple enough. Second, for each of those 0 rows, you write a maxterm, but pay attention here, the rule is inverted. If a variable is 0, you use it as is. If it's a 1, you use its complement. See? It's flipped. Finally, you just AND all of those maxterms together. Okay, back to our puzzle. We hunt down all 5 rows where the output is 0. Let's look at that very first row, all zeros. Using our new inverted rule, the maxterm is just A or B or C. We do this for all 5 of the 0 rows, getting a unique maxterm for each one. Then we just AND them all together. Yeah, I know it looks a lot more complex, but believe it or not, it describes the exact same logic as our much shorter SOP expression. So now we've got two different-looking expressions that do the exact same job. Let's put them head-to-head. Let's have a little showdown to really see the difference.
Okay, here's the breakdown. SOP, on one hand, focuses on the one outputs. It uses AND terms, the minterms, and it combines them with an OR. This creates what we call an AND/OR circuit. Now, POS does the exact opposite. It focuses on the zero outputs, it uses OR terms, the maxterms, and combines them with an AND, creating an OR/AND circuit. They are perfect, beautiful mirror images of each other.
So this leads to the most obvious question, right? If both methods describe the exact same function, why on earth do we need both? Why not just pick one and stick with it?
Well, the answer is pure engineering efficiency. One form is very often much simpler than the other. And here's the pro tip. You can usually predict which one will be simpler just by glancing at the truth table. Our example had 3 ones and 5 zeros. That means the SOP form, which focuses on the ones, is going to have only 3 terms. The POS form, focusing on the zeros, it has 5. And a simpler expression means you use fewer logic gates, which makes the final circuit cheaper, smaller, and faster. It's all about choosing the path of least resistance.
So at the end of the day, SOP and POS aren't really rivals. They're two sides of the same coin. They're two different tools in a designer's toolbox, right? They give you two different perspectives on the exact same problem, and that gives engineers the flexibility they need to find the most elegant and efficient solution. And that leaves us with a final thought to chew on, this whole idea of focusing on the ones versus the zeros, the successes versus the failures. It goes way beyond just circuits. So think about it. When in your own life is it actually more powerful to solve a problem not by defining what works, but by systematically eliminating everything that doesn't? Something to think about. Thanks for tuning in.